Sigma, or summation notation, is a concise notation for representing sums. On the screen, you can see an example of a sum written in sigma notation. Read aloud, this says the sum of I, as I goes from 1 to 7, and it represents the sum 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. In this video, I will present properties and formulas that can be used to quickly and efficiently evaluate sums written in sigma notation. For example, the sum as I goes from 1 to 99 represents the sum 1 plus 2 plus 3 the whole way up to 99. This would be time-consuming to do by hand. However, with the properties and formulas presented in this video, you will be able to evaluate this sum very quickly. Other examples of sums that will be evaluated using the properties and formulas presented in this video are on the screen now. To summarize what is in this video, I will say that we will begin by discussing the summation properties and formulas, which will make the evaluations of sums written in sigma notation much easier, and this will begin at the 145 mark of the video. We will then move to some examples. The examples of evaluating sums using the formulas begins at the 855 mark. The first example begins at 855, example 2, 1255, and example 3 is 1745. Let's begin. First, we will look at two summation properties. These properties do not give a formula for actually evaluating a sum written in sigma notation. Instead, they just provide ways to rewrite a summation in a somewhat simpler form. The first property is based on the distributive property of addition, and it looks like this. This says the sum as I goes from 1 to n of k times a sub I. N can be any integer. K is a constant. When you are multiplying a constant times some sort of a quantity that's in terms of I, that constant can be moved to the front of the summation. So it simplifies the summation by reducing what you actually have to sum. For example, if you're looking at a sum of 2i, as I goes from 1 to 4, this constant of 2 can be moved to the front of the summation, and then all that needs to be summed is the I. The 2 will then be multiplied by the result. In this case, we're just summing I from 1 to 4, so the sum would be 1 plus 2 plus 3 plus 4. That constant of 2 moved out to the front can be multiplied by the result. The formulas for summation will talk about some ways to easily find the sum as I goes from 1 to 4, or I goes from 1 to any number, no matter how large. But if there's a constant in front of the quantity that's in terms of I, this property says that constant can be moved out to the front, and then you don't have to worry about it to the end. You can multiply then that constant by the result of summing the rest of the expression. The second property is based on the associative and commutative properties of addition, and it looks like this. If you have a sum from I equals 1 to any number, any integer, of two quantities that are added or subtracted, in this property, it's written as a sub I plus or minus b sub I, but these represent two quantities in terms of I. This property says that you can break those apart and sum them up separately. Perhaps, when added together, the two quantities would be a little more difficult to sum. This property allows you to break them apart into two perhaps easier pieces to sum up. We will use this property at the end of this video when we do examples of summations. Now that we've talked about these two properties, we'll move on to summation formulas, which will actually give you formulas for evaluating sums. There are 4 summation formulas we will discuss. Again, unlike the properties we just looked at, these formulas will provide a fairly short and simple rule to find the exact value of a sum regardless of how many terms the sum has. These can be very powerful in giving you a way to find large sums quickly. The first rule describes a situation where you are summing a constant. This formula says the sum of k as I goes from 1 to n, k is a constant, n is an integer, is equal to simply k times n. This is easier to understand if we look at an example with some actual numbers. For example, the sum of 3 as I goes from 1 to 10 means that you are going to sum 3 10 times. 3 plus 3 plus 3 10 times. But you don't have to do that. Using this formula, you can find this sum by simply taking 3 times 10. The constant that you're summing times n, times the number of terms that the sum will have. 3 plus 3 plus 3 10 times is equal to 30. This is found a lot easier by simply doing 3 times 10. The second formula involves actually summing some terms that change. Each term is different. There's not going to be like our first example, 3 plus 3 plus 3, every term is the same. This says the sum as I goes from 1 to n of I. This formula states that this sum is equal to, it's based on n times the quantity of n plus 1 divided by 2. Again, let's look at an example with some numbers. The sum as I goes from 1 to 100 would be very time-consuming to compute by hand. This represents 1 plus 2 plus 3 plus 4, the whole way up to 100. This formula will allow you to find that sum very quickly. We'll substitute a 100 for n and get 100 times 100 plus 1, all divided by 2. The result of this rather simple expression is 5,050, which again represents the sum of 1 plus 2 plus 3 plus 4, the whole way up to 100. This formula can be used regardless of the value of n, no matter how large or small it is, to quickly find a sum. The next two summation formulas deal with summing exponential expressions. When summing a series of numbers squared from 1 to any upper bound, the sum will have the form n times n plus 1 times 2n plus 1 all over 6. This is a bit more complicated than the previous formulas, but still much simpler than adding multiple squared terms together, especially when n is very large. The final summation formula I will discuss deals with a number being cubed. This sum will take the form n squared times the quantity of n plus 1 squared all over 4. Again, a bit of a complicated expression, but much, much easier than adding together multiple cubed terms. Especially again when n is very large. This is much more efficient than doing the summation individually. Now that we've talked about some properties and formulas, we will apply those in 3 examples of evaluating sums that are written in sigma notation. The first of 3 examples we'll look at is the sum as I goes from 1 to 27 of 3i plus 2. We will use the properties and formulas discussed earlier to evaluate this sum. Realize the meaning of this is 3 times 1 plus 2 plus 3 times 2 plus 2 times 3 times 3 plus 2, the whole way up to a value of 27 for I. There would be 27 terms in this sum, and each of those 27 terms would actually have 2 terms itself, 3 times the value of I plus 2. The first thing we'll do to evaluate this sum is we're going to use the property we discussed that says that if you're taking the sum of a quantity that has 2 terms, that can be broken apart, and you can find the sum of each term individually. So what I'll do is I'll break up the sum of 3i plus 2 into the sum of just 3i and the sum of just 2, both of those going from 1 to 27, both going from I equals 1 to 27 as the original problem was. Now when you look at the first term of these two, when you look at the first of these two, I'm finding the sum of 3i. We had a property dealing with finding a sum when there was a coefficient, and that property was this. It said if you're taking the sum of anything, and there's a part of it that's in terms of I multiplied by a constant, that constant can be moved to the front of the summation. And that's what I'll do here. I'll take that 3, move it out to the front, and eventually I'll multiply it by the result of the sum as I goes from 1 to 27 of just I. So now that this is broken apart as much as I can, look, we're just taking the sum of I and the sum of 2. We'll go ahead and evaluate each part. To evaluate the sum as I goes from 1 to 27, we'll use the second of the formulas we discussed. The sum as I goes from 1 to n of any I is n times n plus 1. It's based on the value of n all over 2. So here we have a value of n of 27. So that means that this will be 3. The 3 in the front will stay multiplied in the front because n is 27. The sum as I goes from 1 to 27 of I is 27 times 27 plus 1 over 2. Look at the second term now in the sum that we have. The sum as I goes from 1 to 27 of 2. The first formula we discussed is summing a constant. When you sum a constant, you're simply going to multiply that constant by the value of n. So here our constant is 2. The value of n is 27. So the sum as I goes from 1 to 27 of 2 is simply 2 times n, 2 times 27. And now it's just a matter of doing the arithmetic to simplify this. 27 plus 1 is 28, times 27 is 756. 2 times 27 is 54. Using the order of operations, I'll go ahead and do this 756 divided by 2 to get 378 times 3 plus 54 equals 1188. The result of the original sum is 1,188. Again, this is the same thing you would get if you wrote out 3 times 1 plus 2 plus 3 times 2 plus 2 plus 3 times 3 plus 2, the whole way up to a value for I of 27. All 27 of those terms would add up to exactly 1,188. Let's move to example 2. Example 2 involves summing a quadratic. This is the sum as I goes from 1 to 20 of I squared minus 2i plus 1. The first thing that I will do is the same as the first thing I did in example 1. It's to realize we're adding and subtracting some terms here in this sum, and to make it easier to do, we can break it apart into individual terms. We can sum each term individually. So here, that means I can take my original problem and break it apart into 3 individual summations. The first term, I squared. The second term, 2i. The third term, 1. Look at the signs. The signs are going to stay the same. The first sum has a positive in front of it. The second term, minus. The third term, plus. All 3 of these summations are as I goes from 1 to 20. Look at the first term. It is the sum as I goes from 1 to 20 of I squared. We had a formula to deal with summing the square of I. It was the third formula we discussed, and it says that when you're summing a quantity of I squared from 1 to any value, this formula can be used. N times n plus 1 times 2n plus 1 all over 6. So it's all based on the value of n, which in this case is 20. So substituting a 20 for n into this formula, I'll have 20 times 20 plus 1 times 2 times n, 20 plus 1 all over 6. So the result of the sum as I goes from 1 to 20 of I squared, 1 squared plus 2 squared plus 3 squared, the whole way up to 20 can be represented by this expression. The second term involves a sum of 2i. There's a constant multiplied by I. We had a property that said if you are multiplying a constant by some quantity in terms of I, that constant can be moved out to the front. Once we move that constant out to the front, we'll just have the sum as I goes from 1 to 20 of I. And then in that case, we'll use the formula for summing I. We used this formula in example 1. When you sum from 1 to n of I, n times n plus 1 over 2. So here that will be 20 times 20 plus 1 over 2. The 2, using the property of constant multiplied by a quantity in terms of I, has been moved out to the front. The sum of I from 1 to 20 is represented by the fraction 20 times 20 plus 1 over 2. The last term, the sum of 1 as I goes from 1 to 20. We have a formula for summing a constant. It's simply that constant times the value of n. So in this case, that will be 1 times 20. I'll put a plus sign, carry that down. 1 times n, 1 times 20 will be the last term in my solution. So at this point, we have some arithmetic to do. 20 plus 1 is 21. 2 times 20 is 40 plus 1 is 41. 41 times 21 times 20 is 17,220, which I will then divide by 6. Then we have a minus sign, and we're dealing with 2 times 20 times 20 plus 1, 20 times 21, which is 420, divided by 2. And the last term, 1 times 20, is, of course, just 20. So we have 3 terms to deal with. You can use a calculator, do the arithmetic, but those add up to 2,470. 2,470 is the result of the original sum, as I goes from 1 to 20 of I squared minus 2I plus 1. Again, this 2,470 represents the result of doing 1 squared minus 2 times 1 plus 1, plus 2 squared minus 2 times 2 plus 1, plus 3 squared minus 2 times 3 plus 1, the whole way up to 20. The result of that sum would be 2,470. That would be a lot less efficient than using the properties and formulas described here to find the sum using the method described. Now let's do one more example. The final example we'll look at is the sum as I goes from 1 to 42 of I to the third plus 2I. Written out in long form, this means 1 to the third plus 2 times 1, plus 2 to the third plus 2 times 2, plus 3 to the third plus 2 times 3, the whole way up to 42. This sum would have 42 terms if we wrote it out, and each one of those 42 terms would have 2 terms itself. My point is, it would be very inefficient to find the sum using that process. Instead, we'll take this sum and we'll apply the properties and formulas we've discussed to find it a lot faster. Just like the previous 2 examples, the first thing we'll do is we'll break apart each term in the original summation into 2 individual summations, both going from 1 to 42, the first term of I to the third, the second term of 2I. There's a plus sign in the middle of these 2 summations, which carries over from the original problem. When I take a look at the first term of this now broken apart into 2 terms sum, I have an I to the third power. We have a formula for summing an I to the third. It looks like this. N squared times n plus 1 squared all over 4. It's all based on the value of n, which in this case will be 42. Plugging a 42 in for n into this formula, I'll have 42 squared times 42 plus 1 squared all over 4. The second part of this summation, now that it's broken apart into 2 terms, is the sum as I goes from 1 to 42 of 2I. There's a constant in front of the I, so we'll use the same property we used in the last 2 examples to move that constant out to the front, and we'll be left with just the sum as I goes from 1 to 42 of I. And to evaluate that, we'll use the formula n times n plus 1 over 2. Applying that, the coefficient 2 on the I is moved out to the front. Then I'll substitute a 42 for n into this formula, 42 times 42 plus 1 over 2. And now this becomes a calculator exercise, an arithmetic exercise. I will take 42 squared times 42 plus 1 is 43 squared, all divided by 4. One way to approach the next step here would be to realize I could actually cancel out these the 2 in front of the fraction and the denominator. And then this second term can be evaluated by simply multiplying 42 times 42 plus 1, 43. 42 times 43. Doing this arithmetic, the result is 817,215. Very large sum, again, would be very, very tedious and time-consuming to do longhand by writing out a list of the 42 terms from the original summation. Using the formulas, we can find this sum much faster. Thank you for watching. I hope you learned something.